So we're going to use our calculators. So pull your calculators out if you haven't already done it. And let me give you some different ideas on what you should expect from the AP exam, as well as what kind of things you should expect to use in terms of your calculator. Okay. So by the end of today's lesson, I'm also going to talk about some common mistakes. So that's the first thing I'm going to do is talk about what are some common mistakes that AP graders have seen, and it just makes us pull our hair out. Things that I've talked about throughout the year, but things that I want to just kind of emphasize and reiterate to make sure that everyone understands it. Everyone should be able to utilize their calculator to solve calculus concepts. And then everyone should be working on their clue packet, but actually I'm not going to assign the clue packet, so you don't have to worry about that. But there's some excellent questions in the clue packet, which I might actually still give you guys just for practice, but it's not going to be for a grade. But it very much follows a lot of free response questions that you'll see on the AP exam. That being said, the following are some common mistakes that make readers, AP readers, pull their hair out. So number one, if you have something that is arithmetic, right? If you have like 6/9, of course you could simplify 6/9 to 2/3, but you don't have to, okay? So there's no need to simplify arithmetically. However, if you do simplify, you do have to simplify correctly. And if you don't, you're going to lose points. So please make sure that if you're going to simplify, that you do it correctly. Otherwise, don't simplify at all. Just leave it the way it is. Even things that are very long, like a Riemann sum, if you have the whole formula written out, you're done. You could stop. There's no need to do any arithmetic, okay? So you do not have to do any arithmetic. You could just stop, okay? So for free response, you do not have to simplify, which is really nice because we've been simplifying a lot, but when we simplify, we've been simplifying for our multiple choice questions. But as you know, there's no multiple choice questions on your AP exam this year. So you don't have to worry about that. So no need to simplify. Okay, so there's no need to simplify. Number two, unless you know for a fact that everything that you've written is completely wrong, don't cross it out. If you cross it out, we look at it as if it was never written, okay? So if you cross it out, we're gonna say it wasn't written. That being said, please, if you have an answer, don't give two different answers, two different sets of answers. Because remember, if you give two different sets of answers, we call that a parallel solution. And if you give me parallel solutions, then I'm going to choose the one that's wrong and grade the one that's wrong. So please make sure that if you do give two sets of solutions, you cross one out, okay? Because otherwise you're contradicting yourself and you're going to lose a lot of points. Also, always make sure that you're labeling everything. You do have to make sure that, you know, if you're talking about the derivative, you call it f prime of x. If you're talking about the second derivative, f double prime. If you're talking about the original function, f of x, right? So make sure you label everything. And if there's units, make sure to produce units, okay? So if it's unitless, don't worry about it. But if there are units, you need to put units, okay? So if it's a word problem, just know it's going to have units and you must put your answer in terms of units. If you're worried about your results in part A and you know that part A is absolutely incorrect, that's okay. Just finish your answer as if A is correct. So if you're like, oh, I don't think A is right, but I think I could still answer part B, but in order to answer part B, I need part A. Just use whatever you have in part A, and as long as you do part B correctly, we're going to grade part B independent of part A. So that means that whatever answer you put into part A, if you put that into part B and you answer part B correctly, or C or D or whatever, then you could still get full credit, okay? Just to let you know. If you use your calculator, please make sure you're describing exactly what you're doing mathematically. Please don't use calculator speak. And you're going to see what I mean by calculator speak here shortly as I start using my TI-84, as I show you some different things that we could do mathematically in our calculator. Okay. By the way, even if you have a TI-84, you might have a different operating system than me. If you have a different operating system, it's going to look different. Okay, just to let you know. So don't write bad math. So for example, don't talk about the slope of the derivative. If you talk about the slope of the derivative, then you're saying that the derivative is either a line or you're talking about the slope of the tangent line of the derivative. And so you're actually talking about the derivative of the derivative. So don't say things like the slope of the derivative. Okay, remember the derivative is a slope. So it's a slope of a tangent line. So If you talk about the slope of the derivative, you're saying that the derivative is a line and it has a slope, which may or may not be true, right? Don't say things like 6.2368 is equal to 6.237. Those are not equal. Those are approximates, okay? So you have to use the approximation symbol in here. So make sure that if you're going to say that 6.2368, say it's approximately 6.237, okay? So please make sure you're using the approximation symbol. Be careful with your positives and negatives. Don't say that negative 17.21 is equal to positive 17.21, because obviously those are not equal. Okay, so please be very careful. Don't write poor math, because if you write it poorly, then you're going to lose points. So we will definitely dock you for doing things like this. Okay. Remember to go at least 3 decimal places. Now, when I say go at least 3 decimal places, it's at least 3 decimal places for the solution. Okay, so that means you want to go as many decimal places as you can until you get to the solution. Once you get to the solution, then you go 3 decimal places. You have to be careful that you don't go 3 decimal places too early, because if you go too early, you're going to have something called a compounded round-off error. A compounded round-off error just means it's a rounded answer of a rounded answer of a rounded answer of a rounded answer, and it could definitely be nowhere near close then, right? So don't round until you get to the end. Okay, and when you round, you could either round or you could truncate. And when you truncate, that just means you look at the first 3 numbers and you cut out all the rest of the numbers afterwards. So either rounding or truncating are valid and acceptable on the AP exam. Okay, don't write something like this. F of x is equal to 2.15 plus 3. When you mean f of 1.5 is equal to 2 times 1.5 plus 3. If you say f of x is equal to this, you're saying your function is a line, is a constant, okay? So you're saying that f of x is a constant. In fact, right here, for the example, this example, you're saying f of x equals 6, and only 6. It can't be anything else other than 6, right? But if you're saying f of 1.5 is 2 times 1.5 plus 3, or 6, you're saying that it's only 6 at this point. Or we know that at this point, it's exactly 6. It might be 6 somewhere else. We don't know, but we know that at this point, it's 6. Whereas here, you're saying it's always 6. So be very careful. So once again, that goes back to don't write poor math or don't write bad math. Okay. Every pronoun needs an antecedent. Okay. So don't say things like the slope is 7. The slope of what is 7? So if I don't know of what, then you're not writing it accurate enough. Okay, so make sure that you're explicit. So the slope of the tangent line of G is 7. Something to that is much better, much more accurate. And so please make sure that you're stating things accurately. Okay, so be very explicit as to what you're talking about. So when you're writing that down, be very clear what you're talking about. Okay, now why can't I say the slope is 7? Well, I don't know what you're talking about. The derivative, the original function, its antiderivative. Is there 2 functions? Is there a f of x, a g of x? I don't know what you're talking about. And so you have to be very clear what it is that you're speaking of, okay? When asked to write an integral, this is actually speaking of if I put it in a summation form. So if I have a limit of a summation, always start with your limits of integration, then the constants, and then your function, and then whatever your integrand is. Please make sure you know the difference between increasing and positive, right? When the derivative is positive, the function is increasing, right? Or when the function is increasing, the derivative is positive, okay? Don't get that mixed up. When the derivative is negative, right? When the derivative is negative, then the function is decreasing, right? We also know that, so that's the alternative. There's 4 things that you're going to be using your calculator for. So the 4 things that you're going to use your calculator for are: 1, you need to find it to graph, okay? So I'm going to show you how to graph. If you don't already know how to graph, I'm going to show you how to do that using our calculators today. Number 2, you should be able to find roots. So you should be able to find all the places where your graph hits the x-axis, okay? Number 3, you should be able to find a numerical derivative. That means you should be able to find the slope of the tangent line at a specific point. And I'm going to show you that as well. And then number 4, you should be able to find the numerical integration. You should be able to find the area under a curve on an interval. Okay. And then, of course, everyone should know the difference between a local and a global extrema, or a relative and an absolute extrema, right? So you should know the difference between those. So if I ask you for the maximum, or what am I asking you for? If I say, what's the maximum speed, let's say, am I asking you for the relative or the absolute? Okay, good. It's the absolute. So if I don't say relative, it's automatically the absolute, which means, and the way that we find the absolute extrema is you find the derivative, set it equal to 0, find your critical points. You plug your critical points and your endpoints back into the original to see which is the maximum for the maximum, or which one's the minimum for the minimum, okay? If I ask you for relative extrema, you're finding the derivative and then you set it equal to 0 and you do a sign chart, okay? So those are two very different things, and you have to be very clear on how to do both, right? How do you find the local extrema? And how do you find the absolute extrema? Or how do you find the local extrema and the global extrema? Okay. Know the difference between an extreme value and the location of the extreme value. So if I say, where is the maximum? I'm talking about the X. If I say, what is the maximum? I'm talking about the Y value. Okay. So anytime I say, what's the maximum speed? That would be your Y value, right? If I said, where or when do you get your maximum speed? That would be in terms of time, t, and t would be your x value, or your explanatory, or your x variable. Okay, and then when you're justifying your local extrema points of inflection, make sure that you're using a sign chart and that you have it very well labeled, okay? And then you have to use sentences in order to say that. So if you're looking for a relative maximum, you could say that there's a relative maximum because the derivative changes from positive to negative at some point C, right? So if the derivative is changing signs, we know there's a relative extrema there, okay? So be very clear on how you know there's a relative extrema or an absolute extrema, or whatever it is that you're looking for. Okay, so let's go ahead and look at our calculators. So pull your calculators out. Let me give you a question. So here's a question that was on in 2003, the AB exam, and it said something like this. It said, let f be a function with the derivative. So this is the derivative function, sine of x squared plus 1. How many relative extrema does f have on the interval from 2 to 4? So pull out your calculators, and we're going to go ahead and look at this, okay? So the first thing I'm going to want to do is I'm going to want to plug in a function. Our function that we had was sine of x squared plus 1. Okay, so sine of x squared plus 1. So what I'm going to do here, I'm going to go to my y equals. So right here. So if everyone looks at the on button, if you go all the way straight up to the second button and even above that to where it says y equals, we're going to type in our function. So let me go ahead and clear that out. So in my y1, I'm going to type in the function that we have, and it was sine of x, and I'm going to go ahead and use the caret here, x squared plus 1, okay? And then the one thing that everyone should understand is this is our derivative function, okay? So be very careful that you understand that this is our derivative function, okay? And then actually what I'll do here is I'll put our window, okay? So the next thing I'm going to do is I'm going to go to the window. So everyone press this window button or go to your window button. I think if you have a TI-89, it's going to be diamond F2, okay? So diamond F2 or the window button. So I'm going to press this window button. In the window button, we're going to set up our window. Our x's are going to go from 2 to 4. So it told us that we want to be on the interval from 2 to 4. So I'm going to say my x min is 2. And then I'm going to go down and I'm going to say my x max is 4. Okay. So I'm going to go from 2 to 4. Now your x scale is, if you had a number line, what would you count by if you were going from 2 to 4? And I might actually count by a half. I might count by ones. I'm going to go ahead and count by a half just because, you know, I could have a couple of dashes in there so I could kind of follow along a little bit. Okay, so that was my x scale. So your x scale is what you're counting by. My y min, now this is sine. Even though it's sine of x squared plus 1, x squared plus 1 is inside of sine. And so this is sine of something. And so sine, you should know that the minimum that sine could be is -1. So when you do -1, make sure you're using the negative button, not the minus button, okay? If you use the minus button, it's gonna give you an error. So use the negative button, which is right here next to the decimal point, and that's for any calculator that you're using. So you're gonna use the negative, and we're gonna say -1, okay? So that's our minimum y value. My maximum y value is +1. Okay, and then once again, I'm going to count by 0.5. I'm going to count by a half. So Richard asks, how do you do that on the TI-89? It's the same thing. So same exact thing. Okay, so you want to go to your window, and then window was diamond. There's like a green diamond button under the second button. You press diamond F2. It's at the very top, diamond F2, and it's going to go to your window. So everyone type in this window. Don't ever mess with your XRes. Don't worry about this. You might not even have this, right? So if you don't have delta X, don't worry about it. If you don't have trace, don't worry about that either. All that matters is X min, X max, your scale, X scale, Y min, Y max, Y scale. So I'm going to refresh this so everyone can see what I have in my window. This is what my window looks like. This is what my equation looks like. And then if you press graph, it's going to give you this right here, this window, and this right here is the graph of our first derivative. Remember, this is the derivative function. So this is the derivative, okay? So if everyone looks, it's going to hit the x-axis 1, 2, 3, 4 times, which means that this is going to have 4 critical points. So there's 4 places where the derivative equals 0. So there's 4 places where the derivative equals 0. So it says here, how many relative extrema does f have on the interval from 2 to 4? And so this is 2, 2.5, 3, 3.5, 4, because if everyone knows, I'm counting by halves. And then this is a half and 1. This is a half and -1. So our sine function is in between -1 and 1. So this is going to have 4 relative extrema. And not only do I have 4 relative extrema, I have 2 minimums. I know that this right here and this right here is a minimum. And I have 2 maximums, this right here and this right here is a maximum. This is a minimum because the derivative changes from negative to positive. So our function goes from decreasing to increasing. So if it goes from decreasing to increasing, that means that this point must be a minimum, right? So if a function decreases and then increases, that place where it changed from decreasing to increasing must be the minimum. And then this is a maximum because our derivative is changing from positive to negative. If our derivative is changing from positive to negative, our function is changing from increasing to decreasing, which means that this is a relative maximum. Okay, so that's how we would graph it. Now, there's a couple of things that we're going to want to do, right? So I know that there's 4 places where we're going to have relative extrema. Now, the question is, what's the location? Where am I going to have a relative maximum? Okay, so I know I'm going to have a relative maximum here and here. So that being said, how do I actually find this thing right here? How do I actually find that 0? And so if you have a TI-89, you're going to press F5. If you have a TI-84, you're going to just press, it says up here in blue calc. So I have to press the blue button because I want the blue calculate. I'm going to press second and I'm going to do calculate, okay? And then it tells me I could find the value, I could find the 0, I could find the minimum, the maximum, the intersect, dy dx, the derivative, that's the slope at a certain point, as well as the integral on an interval. What I want is a 0. So I'm going to go to number 2, and you could actually just type the number 2 here, and it's going to say, okay, which one do you want? And so I want this first one here, okay? So I want this first one. If I want this relative minimum here, okay? If I want this relative minimum, I have to find a point to the left of it. This is 2. So I have to plug in a value between 2 and 4. So it has to be in the screen. So let me use 2.1. That's 2.1. All right. So 2.1. And then now I have to pick a point to the right of this 0. So since I know that this is 2.5, okay, so I have to say 2.5. And if I press 2.5, that's going to give me my right endpoint. It says guess. I'm just going to press enter. It's not really guessing. It's just going to say it's a guess, but it's not a guess. And so my x value is 2.298. That's going to be my first x value where I have a minimum, right? So that's where I have a minimum. So, and I know it's a minimum because my derivative is changing from negative to positive. I think I might have had some questions in the chat. So let me see if I can see my chat. If you see a line, make sure your mode is in radians. Make sure you're in radians. If you're in degrees, it's totally messed up. You're not going to have that graph, okay? Make sure you're in radians. Make sure you're in radians, okay? If you're in radians, you should see this graph here, okay? So if you're in radians, you should see this graph here. And so this is the derivative graph. It's not the graph of the original function, right? It's the derivative graph. All right, so let me go ahead and find this right here, which is a maximum, okay? So I think the original question was, locate your two maximum points. So let me just go ahead and make that a question. That's not the original question on the PowerPoint, but let me just make that a question for right now. What are the two maximum points? So I know that this is a maximum because the derivative is changing from positive to negative. And this is a maximum because the derivative is changing from positive to negative, okay? So to find this one right here, once again, I'm going to go to calculate, which is second, calc trace, which is calculate in blue right there. And if you have a TI-89, if you press F5, you're going to go to the same thing that I'm going to go to, which is 0. So I'm just going to press the number 2. And I want this one right here. And so I have to pick a point to the left of it, okay? But to the right of this critical point. So I want to point to the right of this critical point, but to the left of this critical point. And so I know this is 2.5. So I'm going to go ahead and say maybe 2.6 or something like that. So I'm going to say 2.6. Okay, and then I have to pick a point to the right of it. Since I know that this right here is 3, I'm going to go ahead and plug in 3 now. So I'm going to say 3, enter. It says guess. It's not a guess. It's actually finding the value, and it's 2.9025. Okay, so that's the value that will give me the maximum. That's what the location of the maximum of the original function. And remember, this is not the original function. This is your derivative function. So now let me go ahead and find this maximum over here. I'm going to do the exact same thing. Second, trace or calculate. I'm going to find the 0, number 2. I want a value to the left of this, but to the right of this. This is 3.5. So let me go ahead and say 3.7. I need a value to the right of here. This is 3. I don't want to choose 3. I never want to use a value at the end. Okay, so you always want a value on the interval, not on the endpoints. Okay, so I'm going to say 3.9. So I'm going to say 3.9. So that's a value to the right, and you should see that this is in between these two lines, right? So this point is in between these two values there. And if you press enter, we're going to get 3.835, and those are the two places where we get a maximum. Okay, now if you look at this, it's saying that this is as close as they could get to 0. So they're at 0.0000, 11 zeros, and then a 1. So they're pretty darn close to 0, but they're not exactly at 0. So, but that's okay. We only have to go 3 decimal places. So this is accurate definitely to 3 decimal places. Okay, so it doesn't matter that, and this is accurate to 3 decimal places as well. The first 3 decimal places are 0. So we're going to say that this is approximately 0. Okay, so when it says guess, the reason why it says guess is because it may not give you 100% accurate, a 100% accurate value, because they're estimating this, and this is only estimating it to 7 decimal places. So it's not that it's really a guess, it's just that it's estimating it to 7 decimal places, right? And then this is going to 12 decimal places, but close enough, okay? All right, so let's go ahead and go back to the PowerPoint. And I believe that I've answered this first question for sure. How many relative extrema are there? We did say that there's 4, okay? In order to answer this question using the calculator, do not try to integrate. So we're not trying to graph the original function, okay? We're using the derivative function. We're graphing the derivative function. Whatever function they give you, that's what you're going to graph, okay? That's what you need to use in order to answer this question. Okay, so you have to graph what they give you. Don't try to integrate this. If you try to integrate this, remember there's a plus c, and so you'll never know what the actual function is. So there's no point in that. We might as well just use the function that they gave us, okay? And secondly, the graph of f prime, we're going to look for the zeros because those are critical values. We're going to determine when it changes from positive to negative because those are going to be our relative extrema. And then if it changes from positive to negative, it's a relative max. From negative to positive, it's a relative. All right, what should our x min, x scale be? Well, we already did that. We already did the Y min, Y max, and Y scale. And everyone should have gotten this graph right here. If you use the TI-89, it might look a little bit more like this, a little bit more black and white, but it's pretty much the same graph. It's going to be the same graph. And here, what I did is I went from -2 to 2, rather from -1 to 1. If you want to kind of zoom out of this graph a little bit to just get a better picture of what it might look like, I like to go a little bit less and a little bit more than what the graph is, usually speaking, because I don't like it to fill my entire screen most of the times. Okay, so what's the significance of these points? Those are critical points. Those critical points are what we're looking for. All right, so let's try that again. So part B says, and this is part of the same question, and this is what you should expect to see on the AP exam. They're gonna be doing a lot of different concepts using one function or something like that. Kind of similar, very similar to what you should expect to see on my tests, right? So I usually do A, B, C, D, something like that. And I do that because it mimics very much the AP exam. So let's go ahead and determine where is g of x decreasing on the interval from -1 to 3. Okay, so when is this function decreasing on this interval? And they tell me g of x is equal to the integral of sine of t squared dt, which I do know what the derivative of this is, right? So if you guys remember, what's the derivative of an integral? And the derivative of this integral x, so d dx of the integral from 0 to x of sine of t squared dt, that's the second fundamental theorem of calculus, which tells us the derivative and the integral will basically cancel, right? So it's going to be, if I find the derivative of this, it's going to be sine of x squared. So that's our function. Our function that we're working with is sine of x squared from -1 to 3. So let's go back to our calculator, okay? So I'm back at my calculator. This time I'm gonna clear this out. I'm gonna quit. Second mode right here is quit. If you have a TI-89, you just press your home screen, just press home. And then I'm gonna go to my y equals again. So y equals. And if you have a TI-89 diamond, so instead of alpha here, you have a diamond. I think it's green, diamond. And then the first button on the top left is your y equals. It should be F1. And then this time our function was sine of x squared. So it's almost the same function, right? So it's almost the same function. So I'm just gonna go ahead here. I'm gonna go over here and I'm gonna delete my 1 and I'm gonna delete my my plus. Don't press clear. If you press clear, it's gonna clear it all out and you have to start all over, okay? So this is going to be, you have to press delete to delete it. So this is our function. This is our derivative function, okay? Sine of x squared, okay? The next thing I have to do is I have to go to my window again. So I'm gonna just press window. For those of you guys who had TI-89, you're gonna press diamond, F2. We're gonna go to a window. This said to go from -1, and I like to go a little bit, I am gonna go a little bit to the left of that. So I'm gonna go -1.5. It did say -1 to 3. So I wanna go a little bit left of that and then also a little bit to the right of our maximum. So it said that our maximum x value should be 3. So I'm just gonna do 3, let's just do 3.1. Let's actually make this one -1.1. Okay, so let's just go a little bit to the left of our graph and a little bit to the right of our graph, okay? So we were supposed to go from -1 to 3, so I'll go -1.1 to 3.1. And then my x scale, 0.5 is still fine. If you want to, you could clear that and just make it 1. That way you don't get confused and you know that every dash is an integer. My y scale, this is sine again. So sine is gonna go from -1 to 1. But let's go a little bit less, a little bit more. So let's just go -1. I'm gonna go ahead and 1.5 to +1.5. That way we could zoom out of this a little bit and I could get a full view of my sine function. Okay, so I could get a full view of my sine function. Okay, so this is what I'm gonna use for my scaling here. This is what I'm gonna use for my scaling. Let me go ahead and graph that now. And then for those of you guys who missed it, I'll refresh this so that you can see everything. So here's my graph. Here's my function. My function is sine of x squared. Here's my window. So you guys can see all of those things right now. And then this is our function. If you remember what the original question was, when is our original function decreasing? And so this is the derivative function. And remember, this is 3, so we don't want to go beyond 3 here. So anything to the right of 3 or to the left of -1 doesn't matter. All we care about is from -1 to 3 up to here, okay? It's decreasing when the derivative is negative, and it's negative here, okay? So right here, this is where it's negative. This is what I have to find. I have to find this interval, okay? So I have to figure out what this point is, and I have to figure out what this point is. So once again, our calculator will do that. It'll find the zeros, okay? So I'm gonna go to calculate. So second trace, calculate, or for those of you guys who have TI 89, F5, we're gonna find the 0. And I wanna find this first 0 here. And I know that this first 0 is right between 1 and 2. So I could actually just type in 1, enter, 2, enter. And then press enter one more time because it's gonna say guess. Right there, 1.772. So we get 1.772. Now we're gonna go ahead and do the same thing, except we're gonna do the same thing for this value over here. So I wanna find the interval where our original function is decreasing. So I'm gonna go second, calculate. I'm gonna find the 0. This time, this value is between 2 and 3. And I could use 3 this time because it's not at the end, okay? So that's why I like to go sometimes a little bit further on both sides, just because if I want to use that point, it's going to let me use that point, because sometimes it doesn't let you use the point if it's on the end point. So be very careful with that. So I know it's between 2 and 3. So I'm just going to say 2, enter, 3, enter, enter on guess, 2.5066. So I'm going to say that this function is decreasing on the interval from 1.772 to 2.506, and I'm just truncating. Truncating just means go 3 decimal places and then just erase everything else, okay? Just ignore everything else. So 2.506, and then I want to justify it. You should always justify your solution, since this is where g prime of x is negative or less than 0, since this is where g prime of x is less than 0, okay? We're going to determine when the derivative of our original function of this integral is decreasing. So we want to know when the derivative of this function is negative. We have to determine our window. Our window was from -1 to 3 for our x's, and our y for sine is always between -1 and 1, unless you multiply it by something. If you multiply it by something like 7, then it's going to be between -7 and 7. And then we're going to consider when it's decreasing, and it's decreasing when it's negative. So here's our graph again. So this is the graph of sine of x squared, or the g prime of x is sine of x squared, which is what we graphed, and it's decreasing from here to here, which was -1.772 to 2.506. Okay. So there we go. And of course you could round it if you want, but you don't have to. You could always truncate. All right. So that's what it would look like for us to use our calculator. And the one function that we've used so far is graphing, or actually we've used a couple of functions. So I said that there was 4 things that you're going to have to use your calculator for. Number 1, graphing, which we've done. Number 2, evaluating zeros or roots, which we've done. Number 3, we're going to have to find a derivative, and we're going to have to find an integral. And I'm going to show you that as well. Okay, so here's another question. It says, let R be the shaded region between these 2 graphs, okay? So how do we find the area in between 2 curves? The area between 2 curves is the area underneath this top curve. So it's this top curve. I have to find the area under that curve, and I'm going to subtract minus the area underneath the second curve. So if I subtract this from the area underneath R, it's going to give us the area between them. An easy way of doing that is it's the area of the top function minus the bottom function. So if you do top function minus bottom function, it will always give you the area in between. So that's just a quick and easy way of doing it. So all I have to do is top function minus bottom function. So the main thing I have to do is look at this and figure out what's the top function and what's the bottom function. So we have a square root of x function, and we have e to the negative 3x power function. And you should recognize that this right here, this top function, is the square root function. which means that this right here is our e function. This is our exponential growth function, but it's actually decay. It's our exponential decay function because it's a negative exponent, okay? So this is our top function, bottom function, so it's square root of x minus e to the negative 3x, and all I have to do is find the area from this point to this point. So the area from this intersection point to this point. So if I could find that, and I know this point is 1, okay, so I know that that's 1. I have to find the area from here to here. So how do I do that? So let's go ahead and look at our calculators, okay? So I'm going to go ahead and show you my calculator. The first thing I'm going to do is I could go ahead and type both of these graphs into my y equal. And so let me show you what that would look like. So if I wanted to do that, square root, there is a square root button. So it's right here. So if everyone looks in blue, it's square root for the TI-84. TI-89, there's also a square root button, except it's the multiplication. It's right above the multiplication. So you have to do second multiplication, and that should give you square root. But if you have a TI-84, it's second x squared. There is no x squared button for the TI-89, so you just have to kind of just do that. TI-89, it's going to be second multiplication. And I'm just going to say square root of x, okay? And then I need to exit out of that, so I have to press to the right, otherwise I'll be stuck in the radical. And then I'm going to go to my second function. My second function was e, and so e is right here, okay, above the ln button, which makes sense because those are inverses. So I'm going to press second e to the x, okay? In the TI-89, it's a couple of buttons down and it's in green. So you're going to press the green button, and I believe if you go 2 buttons down, it's e to the x. And what we wanted here was negative 3x power. So it was to the negative 3x power. That was our function, okay? All right, so that's that. Also, I know that if I looked at my graph, it did tell me what the window was because it gave me a picture already. And the window was 0, and I want to go a little bit to the left of 0. So I'm going to say negative 0.1. Okay, so negative 0.1. And make sure you're using the negative symbol, not the minus, because those are different. Okay, so I want to go a little bit to the left of 0, and then it went to 1, so I'm going to say 1.1. Okay, and my x scale is just going to be 1, by the way. So I'm going to go ahead and say negative 0.1 again. Let me go ahead and delete that. My y max was about 1, so I'm going to say 1.1. And then I'm not going to mess with anything else. Let me graph this, and then I'll refresh this, so if you missed any of that, you can go ahead and type it in. So I'm going to graph it. There's my square root function, and there's my exponential function. And by the way, if I go to my y equals over here, you can see this is in red if you have a colored TI-84. This is in blue. And then when you graph it, it always goes in order of how you wrote it. So whatever it was in your y1, it's going to graph that first. Whatever's in y2, it's going to graph that second. So that's another thing you could do. Okay, so you could look at that. Another thing you could do is you could press your trace button. And if you look, that's on the blue one. And up here, it tells you y1 equals square root of x. It tells you what function you're on. So if I press down, it's going to go to the red function. And the red function is y2, and it's e to the negative 3x power. Okay, so I know the TI-89s don't have color, but it still does the same thing. It's just in black and white. But it will tell you what function you're on. Okay, it will tell you what function you're on. Now, what I want to do is I want to figure out where do they intersect. I want to see what is this point over here that it's close to, right? What's this point over here that's close to? And I could use my trace button, and I could actually just keep pressing to the right until I get close. I could go, oh yeah, that's pretty close, right? That's pretty close. And it's about there. It's about 0.2. Okay, but I'm going to tell you right now that there's a better way. And the better way is to let the calculator calculate it. So we're going to go second trace or calculate again. So same value, same thing, except this time we want the intersection. So right here, intersect, that's the intersection. So that's number 5 for the TI-84s. If you have a TI-89, you're still going to look for your intersection. It's the same thing. I'm going to press number 5 here. And it says, what's the first curve? What's the first function that we had? And the first function that we had was our y1, which is radical x. So I'm going to press enter on that. Second function, what's the second function? Well, it's this one, this y2. And if you had more than 2 functions, that's why this is important, that you make sure that you find the right function. Because if you had 4 or 5 graphs, you just want to make sure that you're on the right graph, right? And it's going to say guess, but it's not really guessing. It's actually doing a system of equations, and it's actually solving it. And it says the intersection is 0.238, 0.2387, which, if you guys remember, that was exactly what close to what I said it was when I was using my trace function, except this is so much more accurate, and that's going to be a much better value here. And so I'm going to go ahead and use 0.23873, okay? Now, how do I find the area between these two curves? Well, that's a lot harder. What I have to do is do something like this. I'm going to go ahead and do second calculate. Like, look, I'm going to do second calculate. And remember, our value here is 0.2387. So you have to remember that. Okay, 341. And I'm going to just have that written down somewhere. So I'm going to go ahead and press second calculate. And then right here, number 7 is the integral. That's the area. So I'm going to do 7. Okay. And it says the lower limit. Where do I want to start? And I want to start right here. So I'm going to type in 0.2387341. I press enter. Okay. So that's right there. The upper value, I want it to go all the way to 1. So I'm just going to press 1. Enter. And look. It finds the area under the curve. The area under the curve is 0.5889. Like, look at how amazing that is, 0.5889. That's the area under the square root function. But that's too much. I didn't want all of this, right? I want to get rid of this area under the red function. So I still have this red function. I still have to get rid of that area. So I have to subtract the area under the red. So how do I subtract the area under the red? So, so I have to get rid of, if you look over on the side here, I have to get rid of this area under the red. I actually have to turn this function off. So I'm going to go over here where it says equals, press enter on that, and it actually turns it off. Okay. So if you look here, when the equal sign is not highlighted, the function is off. When the equal sign is highlighted, the function's on. If you have a TI-89, actually what you want to do is press F4. F4 has a check mark, and it'll put a check mark if it's on, and then the check mark will be off if it's off. Okay. So sorry. So this is going to give me this function here, and then I could calculate, and it was 0.2387341 to 1. Okay. And then that gives me the area under that curve, and I just have to subtract that from the area that we got for the radical, okay? So if I just subtract those, that will give me the area between the two curves, okay? Now, the question that you should be asking is, isn't there an easier way than doing it? And yes, there's an easier way. What's the easier way? Let's just turn this into a difference. So I'm going to say here, radical x, and so I did say that I can make this, I can simplify this just by subtracting them. So I'm going to say minus, and I'm going to minus e to the negative 3x power. So e to the negative 3x power. And I'm going to go ahead and clear this one out, so I don't need that one anymore. The window doesn't change. The only thing that changes is now my graph. So my graph is going to be a single graph, okay? So what does this graph represent? This graph represents the area between those two curves. This right here, that's what that represents, the area between those two curves. And guess what happens when I find this 0 right here? When the difference between them is 0. That's the intersection point. So look, if I just go back to calculate, and now going back to a 0 rather than intersect, go back to a 0. And I want to find a value to the left of this, and I know a value is like 0.2. And then a value to the right of this is going to be like 0.4. And then if I press enter, 0.2387341. That's exactly the same x value that we've been using. That's already the x value that we've been using. So it's the exact same x value. And so now, look, all I have to do is calculate the area under the curve. I'm going to calculate the area under the curve from here. I'm just going to press enter. Because once you're there, you could actually press enter. It's already in your x value to 1. I want to go to 1. And now this is going to give us the difference. It's 0.4426. So if I took that 0.5 something and subtracted my 0.17 something, it gives us 0.4426. That's the area between the two curves. It just automatically gives it to me. It's so much easier if I just turn that into a single function rather than working with two separate functions. So rather than working with two separate functions, I could just do a single function, and it's going to give us the area between those two curves, and it will integrate that for me. Okay. So we have to find the intersection, and the intersection is when they're equal to each other. So if you think about it, if you subtract one of these, it's when the difference is 0. That's also an intersection point, right? And was 0.238734. So to find the area, all we have to do is go from the intersection point to 1, because that's what this graph does, is it goes to 1 right there. It shows us 1 of the difference, and our calculator will calculate that. And so in this case, it's 0.443 units squared, because we are talking about area. So make sure you're talking about squared units. Okay, so whenever we're in area, make sure you're talking about squared units. Okay, so a couple of tips here. Don't round off until the end. If you want to, you can actually store your answer into your calculator. And we're going to work with the calculator a lot more. I'm just letting you know, okay? And I'll show you how to store. Just remind me to teach you how to store stuff if I haven't already done that. On the calculator portion of the test, which will probably be the whole thing now, you will not have to show integration steps. So you can just show the answer. So if you look at what I did for my answer, okay, I just said this is approximately this. Make sure you say approximately. Do not say equals unless it's exactly equal to something. Okay, so say approximately. You don't have to show any work. You could just show this, approximately this. That's it. Your calculator is calculating it. Don't have to show any work. Okay, so you can just show that. But you're getting your points in the setup. Did you set this up correctly? If you set this up correctly, that's where you're getting the majority of your points, just to let you know. Okay. Use proper calculus notation. Okay. So if you noticed on the TI 83 and 84, if we go back to it, which I'm not going to right now, just because it would just take too long. It had a certain notation. It said integral of f of x or something like that, f of x dx. You don't want to use that. You don't want to be generic. You want to use the actual function. You want to use proper calculus notation. Don't forget dx, because without dx, that's not area. That's only a distance. And so make sure that you're calculating this correctly. You have approximation, you have an answer, and you have the units. Okay, so that's all very important stuff. Let's go ahead and use a calculator to evaluate. Okay, so what if I ask you to evaluate? So now it says the velocity. So we've seen velocity before is 3 plus 4.1 cosine of 0.9 t. What is a of 4? Okay, so what's the relationship between v and a? What's the relationship between v and a? And v is velocity. A is acceleration. If you guys remember, a is acceleration. What's the relationship between velocity and acceleration? And everyone should say acceleration is the derivative of velocity, right? It's the derivative of velocity. Okay, so how do we use our calculator to do this? Can our calculator do this for me? And the answer is yes. And this is actually not hard. We could do this without a calculator. But if you're allowed to use a calculator, let's use a calculator. So we're going to use our calculator to do that, okay? So I'm going to go ahead and type this into my calculator. So everyone do that right now. So type that into your calculator, into your y1, okay? So everyone type that into y1. So y1 is 3 plus 4.1 cosine of 0.9. It says t here, but we're going to actually put an x, okay? So we always use x for our graph, okay? So I'm going to go ahead and switch over to my calculator so everyone can see exactly what it is that I wrote. So in my calculator, everyone should see this. Y1 is 3 plus 4.1 cosine of 0.9x. So everyone should type that in, okay? After you type that into y1, the only thing that we have to do is we have to know what our window is, okay? So it did ask us to evaluate a of 4, okay? So that means I'm gonna go ahead and choose a window, and then remember, cosine times 4.1, the maximum that cosine could be is 1 times 4.1 is 4.1. Cosine could also be negative 1. Negative 1 times 4.1 is negative 4.1. So if I do 3 plus 4.1, that's 7.1. 3 minus 4.1, it's negative 1.1. Okay, so I'm gonna go ahead and change my window. Okay, so I'm gonna change my window. I want 4. I want a value close to 4. So I'm just gonna say 3 to 5. Okay, so it really doesn't matter what x values you use. You just wanna make sure 4 is in there. Okay, my y is important though. So I said it could be negative 1.1. So let me just do negative 2. And I said it could be 7.1. So I'm gonna say 8. Okay, so negative 2 to 8. It's fine if you're a little bit above or below. Okay, I'm not changing my y scale or my x scale. I'm not changing my x res. Never change that. Never change this delta x. Just leave it the way it is. I'm gonna graph, and there we go. Okay, and I'll refresh that so everyone can see both my equation, or all three: my equation, my window, as well as my graph. Okay, so you should be able to see all of it. All right, and then unfortunately that block is supposed to be a 3. In any case, so here's our graph. I want to evaluate the derivative when x equals 4. So right here, I could draw a tangent line right here, right? I could draw a tangent line right at that point. But I need to know what the derivative is at this point. So how do I do that? So we're going to go to our good old friend, calculate. And if everyone looks here, for me, number 6 is dy dx. And everyone should know dy dx is derivative, or slope of a tangent line. So I'm just going to press the number 6. And I want it when x equals 4. It's right there, right in the middle. Press enter. There you go. dy dx, 1.6329. So I could truncate that and just say 1.632, or I could round it to 1.633. And that's it. That's the slope of my tangent line at that point. So now look, I have a point 4, negative 0.6767, and I have a slope. So the equation of my tangent line, if you think about it, here's the equation of my tangent line. Equation of my tangent line is y plus 0.676 equals 1.632 times x minus 4. So from here, we can write the equation of our tangent line. It gives us everything we need, and that equation will draw a tangent line here. In fact, let me go ahead and do that. Okay, so let me go to my y equals, and right here in red, I'm gonna say it's going to be, let's see, my slope was 1.6329. That was my slope times x minus 4. And then don't forget, it was y minus, so I have to add my y-intercept. So minus 0.6767. All right, so now let me graph that. Oh, look at it. There is the slope of my tangent line at the point 4, right there, right? So pretty amazing, I think, pretty cool. And so now you know all the different things that they expect you to be able to do using your calculator. That's it. Those are the 4 things, right? So you should be able to graph, you should be able to find the intercept as well. Well, I guess you should find the intercept as well as your zeros. You should be able to integrate, and you should be able to differentiate using our calculator, which is really kind of nice and neat that your calculator will just automatically do that for you. You could also do this from the home screen. And in the home screen, you could actually do n-deriv. And so n-deriv, if you use your home screen, what you would do is there's a button called Math. You would click the Math button. And if you go down, it's, I believe, number 8. In your TI-84, there's a Math button, and you would just do n-deriv. But the TI-89 could just do so much more. It's just so much better. And I'm really sorry, but it is. And I will show you something like that on the next time. But right now, you can use your n-deriv. I think on the TI-89, it's second 8. If you do second 8, it's a D, and that D just means derivative. And then you would do the same thing. Type in your function, comma x. You have to tell it with respect to what variable. That's kind of like dy dx. It's like letting it know what variable it's with respect to, and then you have to say what value it's at. In the TI-89, you won't use this. You won't do comma 4. You'll actually close it, and then you'll do the such that button. Such that is right next to 7, and then x equals 4. And so that's our function. That's our variable. That's our particular value. This is what it should look like. So excellent. So it should be ddx, which is d. You're going to type in the function comma x, close the parenthesis. This such that button, this line means such that. It's the button right next to the 7. And then x equals 4. And then it gives you 1.63229. Now, for those of you guys who have a TI-89, if you do the function comma x comma 4, it actually is going to find the 4th derivative. So if we go back to Simpson's rule or Simpson's error, and you want to find the 4th derivative, this will actually find the 4th derivative for you. It'll just automatically do it for you. It just tells you, and I'll tell it to you in terms of x. So if you think about that, that's crazy and amazing. It won't just evaluate. It actually finds the 4th derivative for you. So TI-89, just so much better. Sorry, that's just a fact. All right. So don't make the common mistake of putting t equals 4, okay? Don't say t equals 4 because our variable here is x, not t, okay? So our variable is x, not t. So make sure that you say x equals 4, not t. And then please don't plug in 4 into your x's before you find your derivative. You have to do the derivative first and then find the value at 4, okay? Because if you plug in 4 first, it's a constant, and derivative of a constant is 0, right? So anytime you get 0, you should say, oh, that doesn't seem right. It might not be right. Okay, so I'm almost done here. I only have a couple more questions, but I just want to make sure everyone's comfortable with this. So let's say, for example, I want you to find the average velocity. So this is the average velocity. If you remember, how do we find the average value of something? The average value is 1 over b minus a times the integral from a to b of f of x dx. Okay, so this is our f of x function. So let's go ahead and use our calculator to that. So I'm just going to integrate this from 0 to 3, and I'm going to multiply it times 1 over 3 minus 0. I'm going to multiply it times 1/3. So it's 1/3 times the integral of this function. Okay. In my y equals, I'm going to put in this function. So let me clear out these other ones because I don't need them. And our function was e to the t times t e to the t. Okay, so it's going to be e, and we're going to just do e to the x. Okay, so e to the x plus x times e to the x. Okay, so that's our function. And our window, I'm going to just tell you right now, our window is going to go from negative 0.1, so I'm going to go a little bit less than 0, to 3.1, a little bit more than 3. My y value is going to go from negative 0.1, and it's going to be rather large. I would imagine that it's going to be, I don't know, maybe less than 20 or something like that. Okay, so if I do that and I graph it, oh, so it goes off of the screen. If it goes off of the screen, then that means I need a bigger y value. Okay, so let me actually make this 100 and see if that's better. But if I go by hundreds, I don't want to count by ones. I'm going to count by tens because that's going to be ridiculous to count by ones. And there we go. So the whole thing is in my screen. Okay, so now what I'm going to do is actually something a little bit weird. I'm going to actually insert 1 over 3 times this, because remember, that's what we want, is 1/3 times the integral of this. And remember, 1/3 is just a constant, so it doesn't matter if I put the constant inside the integral or outside the integral, it's going to be the same thing, which actually will make my graph smaller. And so maybe I only need to do 1/3 of my window. So maybe instead of 100, maybe do 30. Okay, so I could go to 30, and then now if I'm going by 30s, I could count by 5s maybe. So that's better. Ooh, that's close. That's really close. Let me do 35 because that's too close. Okay, and then now I just want to find the area under this curve, right? So I want to find the average value. So it's the integral. So I'm going to do second trace, the integral number 7 from 0 to 3. And it's going to shade it, and we get about 20. And so that does all of our division for us. It does everything for us. 1/3 times the integral of our function is about 20. So the average velocity is about 20 units per time, whatever the time factor is. I don't know. Okay, so it's in units per time. Okay, right here, it's our average value is 1 over b minus a times the integral from a to b of f of x dx. We can use a calculator. We can do it from our home screen, but I don't suggest you do it that way. We can do it in our home screen on the TI-89 as well, except once again, I don't suggest that you do it that way. I suggest that you use the calculator, and you should get about 20.0855. The nice thing about the TI-89 is it'll actually approximate it, or it'll give us the exact value if it can, and E cubed is the actual answer here. So it's actually E cubed. A pizza with an initial temperature of 350 changes at a rate of this, determine the temperature after 5 minutes. So this is our initial, and actually we're going to integrate this. If you integrate this, it's going to determine the total amount of temperature change from 0 to 5, okay? And then don't forget, we're starting at 350, so we have to subtract this. This is negative, so 350 minus the total amount that it changes. So this right here, if we integrate this from 0 to 5, it'll give us the total amount it changes, so we're going to subtract that from 350, and it's going to tell us what the temperature is after 5 minutes. So if we do that, it's going to be our function. And so another way you could say that is the integral of our function is the fundamental theorem of calculus, f of b minus f of a, which in this case is t of 5 minus t of 0. And remember, t0 is our temperature at the beginning, right? So 350 is our initial temperature. T5 would be the temperature that we're looking for. What's the temperature after 5 minutes? And so if we add this to this side, it becomes our integral plus 350, which is what I was saying earlier. And so just using our calculator, we could calculate that, and I'll let you guys practice that. And if you do that, you should get 112.217 degrees, and we're in degrees Fahrenheit. Okay, and so this is what it would look like if you used your calculator, and we get something that looks like this. And this is if you have a TI-89, of course. So in short, demonstrate that you actually know calculus. Use calculus notation, not calculator notation. Never use something like this. If I saw something like this in the AP Calculus exam or AP Stat exam, I would just mark that wrong, right? At least in the past, that's been the case. Don't use something like, I used the trapezoid form program. No, you have to actually show your work. Remember, verbal explanations, the function is going up, therefore it's increasing. Don't say things like that. The function is increasing because its derivative is positive, right? We want to use calculus terms and notations. So the derivative is positive, so the function is increasing. And that's pretty much it. Well, I hope this was helpful. Thanks for watching. Bye for now.